Now we are going to discuss the most important topic related to these conductance terms which we have described so far. Now we need to understand before we study the Kohl Rasch Law that the conductance increases with increase of dilution. This is not valid for K because it decreases with increase of dilution. The reason being the decrease in number of ions per unit volume. That is the reason why K, the term K, what is that? The specific conductance is going to decrease with increase of dilution, whereas the other conductances are going to increase with increase of dilution or decrease with concentration. So in a way we are saying that lambda m or lambda E is going to decrease if concentration is increased. Concentration is increased means dilution is decreased. So increase of dilution is increase of conductance, decrease of dilution is decrease of conductance, decrease of dilution means increase of concentration. So these two are inversely linked, hence when I write the relationship between the molar or equivalent conductance with the concentration, I will write it like this, where A and B are some constants. This is valid only for the strong electrolytes. What do I mean by strong electrolytes here? I am talking about strong acids like HCl, strong bases like NaOH, and soluble salts, water soluble salts like NaCl, AgNO3, etc. Now when I am talking about the strong electrolytes, you are going to conduct vigorously, this relationship is valid, which clearly depicts that lambda is going to decrease if you increase the concentration because there is a negative term. Now when I am plotting a graph to show this variation, lambda versus square root of the concentration, as you said, it is decreasing. This is valid for the strong electrolyte, the above case. Now you can see here when I am extrapolating, when I am extending this, I am getting the conductance of the solution at zero concentration. Zero concentration here is referred as zero concentration. We are not going to use, rather we are going to use here a term known as infinite dilution, that you have diluted the solution to such an extent that the concentration has become almost zero. Now when I am extrapolating this, you can see the intercept of that is turning out to be the lambda at infinite dilution. We are going to show it as lambda naught, and here when I am substituting over there, lambda is turning out to be lambda naught minus something into square root of c. And now you are going to find out that slope, you are going to find out d lambda by d square root of c, or you will be finding out by using tan theta. This relationship is valid, my dear friends, only for the strong electrolyte. Now when it comes to the weak electrolyte, what I mean to say is weak acid, weak base or insoluble salt, this relationship is not valid. Rather you will be getting the exponential relationship between these two. Obviously even for the weak electrolyte it is going to affect, but that is not linear relationship as you found there, it is exponential relationship, where you will notice that this y coordinate is always parallel to the y axis, it is never touching it. So extrapolation of this curve will not fetch us the lambda naught value. So in order to find out the lambda naught for the weak electrolyte, we will be taking the help of the Kohl Rasch law. As per this law, the conductance of the electrolyte, no matter whatever you take, the conductance of an electrolyte, which electrolyte we are talking about, whether it is strong or weak, the conductance of the electrolyte at infinite dilution is the arithmetic sum of the conductance of all ions present in it. You can see here when I take this, you are going to split into x moles of M plus Y, because here there are x moles of M whose valency is Y, plus y moles of n minus x. That means the conductance of the salt is the arithmetic sum of these two. So when I write lambda naught of Na2SO4, how would I write? Equal to 2 times of lambda naught of Na plus lambda naught of sulfate ion. When I am writing the conductance of magnesium phosphate Mg3PO4 taken twice is equal to 3 times of lambda naught of Mg plus 2 times of lambda naught of phosphate ion. Even when I am writing the lambda naught of the weak acid at infinite dilution, I will write it as the sum of the lambda naughts of these two. Now by using these relationship, we can find out, we can have certain application related to this Kohl Rasch law, which we are going to discuss now. Yeah, the major obstacle for the weak electrolyte, as we found from the graph, is that by the extrapolation we could not get the lambda naught for the weak electrolyte. Now what I will do is, I will take the Kohl Rasch law. With the help of Kohl Rasch law, I am going to find out the lambda naught of the weak electrolyte. For example, I have the lambda naught of acetic acid to be obtained, for which I will take the help of the strong electrolyte, for which I can do it by means of extrapolation. Then I will eliminate the unwanted term. You can see I have acetate ions here. I want H ions, for which I will take HCl, and here perhaps we will be removing the NaCl component from it to get the lambda naught of acetic acid. Similarly, if you take the lambda naught of NH4OH, it's a weak electrolyte, weak base. I'll take a strong electrolyte of it and I'll cleverly remove the unwanted components. You can see here I have removed here NaCl from it. Say you want to find out the lambda naught of EgCl, you will be doing lambda naught of soluble salt plus something like HCl, and you will be eliminating HNO3. Similarly, dear students, you also practice for barium sulfate, lead sulfate, silver dichromate, which are the precipitates or insoluble salts, by using the Kohl Rasch law. You can see here you will be given these values, just you need to substitute to find out the lambda naught of a weak electrolyte. So Kohl Rasch law is really useful here in order to find out the lambda naught of the weak electrolyte. Can you see here clearly? Yeah. Now when it comes to the second application of this, second application is to find the degree of dissociation of weak acid or weak base, and simultaneously I will be finding out Ka or Kb of the weak acid or weak base. Now I will take acetic acid for an instance. I will take acetic acid whose concentration is C mole per liter. It will not completely dissociate in water. The initial stage I have taken C mole per liter of this, and at equilibrium I found that the degree of dissociation is something like alpha. That means the fraction of the C which has underwent the dissociation. So the remaining will be 1 minus alpha, right? So alpha is the amount that underwent the dissociation. Out of 1, alpha has gone. So remaining is 1 minus alpha of how much? The C moles, right? So this is of you write. Now at infinite dilution, now this will become 0 because I have added water to such an extent that the entire reaction has gone in the forward direction, C and C. Now at equilibrium, the conductance say is lambda, that is the maximum conductance that we can obtain under normal conditions, is directly proportional to the concentration of the ion that are present over there. At infinite dilution, the conductance is referred as lambda naught, is directly proportional to the concentration of the ion that is present over there is C. So therefore, when I divide these two equations, I am getting alpha. You can see when I am dividing it, alpha is lambda upon lambda naught. So we will use this K by C concentration to find out lambda, and we will use this relationship to find out the lambda naught of acetic acid. So this is second application of the Kohl Rasch law, and so far whatever the questions are asked in these entrance examinations are purely based on the Kohl Rasch law as far as the conductance component of electrochemistry is concerned.